Hey everyone, so today we're going to cover section 7.5 in Thomson, the Rosenbluth formula. It may sound a little bit, it's like, wait, what is this formula we're talking about, right? But it brings up a extremely important way for both theoretical and experimental particle physics deal with systems that are more complicated than just scattering two direct fermions off each other. So it's both a extremely useful in if you're doing analysis at the end when we get to it, and also like how do you theoretically like decouple one type of interaction to another. And in fact, what we're gonna see today in the Rosenbluth formula is actually there are current experimental development, not concerning the protons and neutrons, but actually concerning muons, which is also has this thing called the um, anomalous um, magnetic moment that's people have been like debating whether or not is the measurement people are making are real or not, and compared because the theory and the measurements actually disagree with each other, and we'll see how that gets resolved, and you actually would understand why there's this big concern between on this anomalous muon moments, muon magnetic moments, um, and how that either could be like beyond standard model physics, or right, or it's just people either making the measurement in not correctly, or right, or the theoretician not running their doing their calculations correctly. Okay, so it's actually there's a link to the video in from a YouTuber who talks about this issue currently right now, but they're just this has been going on for years. Okay, so let's talk about what this formula is. Let's go back to our book. Okay, so in the previous section we found that the cross section, let's do that in red. In fact, what I'm going to do is I'm going to do a blue pen so that way I never have black pen anymore. Okay, the cross section we found for scattering an electron off a proton, and these are fairly arbitrary particles. I could scatter the same thing with a muon, with a tau, even with quark. That brings into play other things, but yeah, but scattering a fermion off an elementary fermion off a composite particle such as a proton. Okay, this cross section is going to be proportional to alpha square at the leading order as usual. There's the outgoing energy, incoming energy. So this is basically like PF and PI, right? That's in our cross-sectional calculation. Not only that, you get this sine to the fourth power theta over 2, which is from the Rutherford scattering. And then we have cosine square theta, right, which is from the Mott scattering part, right? We just keep modifying this so that we get more different, let's just say, we have additional form factor attached to this. Okay, and then last time when we did the high energy version of this, what happened is that we pick up this additional term, and this is the magnetic spin pairing term. Okay, where is proportional to q squared. Remember, q squared is the opposite. Sorry, capital Q squared is opposite of negative q squared. So it's just to make the sign always positive. So this term always contribute positive to the cross section, and then sine squared theta with sine squared theta towards the end. And you can actually decouple these things, and we're going to see how the Rosenbluth formula does this. Okay, so in the Rosenbluth formula, we're just going to prop this down right away. We're going to try to decouple the electric, or actually known as the charge coupling, right, and the magnetic coupling between the two fermions. Remember, as at very, very low velocity, right, is the charge that dominates the interaction. But as the relative speed between the proton and the electron increases, right, the magnetic part actually picks up because they're both spin 1/2 particles. Okay, so what we're going to do is we're going to translate this directly down to the Rosenbluth formula. Okay, you have the same alpha square, E3, E1, all the stuff in front is the same, signed to the fourth power, right, in the denominator. Okay, we're going to stick in front of here. Okay, we're going to stick basically this form factor, okay, GE, and GE is the electric charge form factor, and then GM is the magnetic magnetic spin form factor. Okay, there's going to be a little factor here called tau, and this is going to allow us to gauge how big of a momentum exchange is between the electron and the proton. And in fact, tau is actually going to be q squared divided by 4m squared of the proton. Okay, and this comes from the fact that when we stick this in front of, we also stick this in front of this gm in front of the sine square term in the previous cross section. Therefore, right, when gm is basically 1, right, if you stick this in here, you're gonna get the previous result we had. Okay, right. So we have GE, GM. One thing to note is that both of these are going to be functions of the momentum exchange between the two particles. Okay. In fact, right, what these form factors are actually doing is accounting for the non-uniform charge distribution of a proton, for example, right, and also the magnetic charge, magnetic distribution. I don't even want to say magnetic charge because there's no such thing as a magnetic monopole. Okay, the magnetic distribution, basically how the magnetic fields are distributed in this proton. Okay, and the way to calculate this, the way to think about this is that you're actually doing what's known as the Fourier transform of the charge distribution, which gives you q squared, right? Which gives you the electric charge form factor, and then if you do a Fourier transform of the magnetic moment of this of whatever particle we're talking about, then you get the magnetic form factor. Okay. All right. And now we're going to have to talk about how these things are normalized to each other. Okay. The charge distribution is going to be normalized to 1. So we're, whatever, when if q squared is equal to 0, when there's no momentum exchange between the two, it should approach 1. Okay. Well, we're going to normalize it so it approaches 1. Okay. For the anomalous and non-melless magnetic moment, okay, we're going to define it as basically 2.79, right, and we're going to see how that's a weird number, times the charge of the elementary charge, which is charge of electrons and protons, okay, divided by the mass of the proton times the basically the spin of this, okay, right, the total spin of this, okay, right. The 2.79 is due to this internal structure of the proton that you can measure experimentally. Okay, let me make this a little bit bigger. In fact, I made the fonts a little bit bigger. Okay, that the magnetic moment of the anomalous magnetic moment of a proton is actually 2.79. For the neutron is actually negative 1.91. Okay, and then for any other fundamental particle, it's supposed to be 2.0 exactly. Okay, since there's no structure inside the muons and electrons and taus, right? So what happened is that when you do this in the first order approximation, you're going to get exactly 2. However, there are corrections to this in the orders of 1 part per million. Okay, and this is actually known as the anomalous magnetic moment, how is this number different from 2? So usually people ask for, as opposed to mu, they want to get actually mu minus 2. So therefore, they should be 0. Okay, but this book is using it. Other people has used different nomenclature, and generally the particle physics community use G instead of mu. It's just an easier number for people to understand instead of these Greek letters, right? So G minus 2, and whenever you see an experiment with a result, a new measurement of G minus 2 for whatever particle we're talking about, that's what they are trying to measure. Okay, how close is it to exactly what the first order approximation for direct fermion? Okay, and in fact, this is a 20-year-old puzzle that's almost solved these days. So there's actually a video by one of the YouTubers, Sabine Hofstetter, that talks about like a very recent result. I think it's like from a couple of weeks ago, where people are now thinking, oh, maybe people just didn't do the pion correction to this pion loop corrections to this calculation. So we'll see how that turned out. So this is a story that's actually running. So and unfortunately we don't have for the so yeah, this is just a still currently running story, and then we'll find out who's right. Whether it is, well, we're not trying to find out who's right, to see where the disagreement between the theoretical calculation and the experimental result is. Okay. All right. So how do we measure these? Going back to the magnetic and the electric charge form factor, right? GE and GM. Right. In order to measure these form factor, what we need to do is actually kind of like factorize things, and this is a really, really neat method, and you're going to use this is useful in a lot of different not just in particle physics, in any data analysis field, where you're trying to factor things out in a way that you can tease out one particular parameter, and then you do the opposite to tease out the other parameter. Okay, so to measure the GE, which is the electric charge form factor, right, this factor here, okay, we're going to work in the regime where, right, the recoil, this Q square, is going to be very small. Okay, why do we want this to be very small? Okay, remember that Q square is, 1 over 2 the mass of the proton, E1 square, and then you have another mass of the proton plus E1, and then it's all multiple, well, this factor and this factor here, right, multiplied by 1 minus cosine theta, right? So what you can do is that, well, if theta is pretty close to 1, right, this means that cosine of theta is pretty much 1. Sorry, theta is close to 0. If theta is close to 0, cosine of theta is 1. So therefore, 1 minus cosine of theta is almost 0. So that allows you to pick out events that has very low Q square. In other words, right, your electron coming in and then your proton coming out. Well, right, P4, P1, okay, and this is P3. Oops, I'm going to draw it like this, right, P3, okay, right, this P2 sitting still there. What happens is that if this angle is very small, right, you're going to have events that has very low Q square, okay. Why do we pick events that have low Q square? Right, remember Q square is also related to this tau factor, right? So if Q square is very small, tau is also very small, right? Okay. What happens is that when tau is very small, right? So this factor basically goes away, this factor basically goes away, this factor basically goes away, right? D sigma, D omega basically becomes, right, whatever GE square is times cosine square theta. So basically what you end up with is the Mott's formula, right, with this form factor in front, okay? Okay. In fact, right, we're going to use this for the Mott scattering formula, right, as a way to probe how does this cross section evolve at, even though with small, the small q square, right? How does it evolve, slightly as you move around a small range of q square, so that you're actually probing how this behaves. Okay. All right. So in fact, what we're going to do is we're going to factorize this. So basically, you do this, right? Right. We know that. Oops. Let me do this. Right. This whole factor, whole thing here, right? Right. All this green stuff, right, is actually the Mott scattering, right? D sigma d omega. Okay. In fact, we're going to call that d sigma d omega naught, because that's the Mott scattering. Okay. And what happened is that, oh, you wrote down here already. Okay. So if you divide whatever cross section we have by the Mott scattering cross section, we're basically going to have G squared, GE squared. Okay. And remember, this is always going to be a function of Q squared still. Okay. Right. And we're going to see this in a little bit of data when we get to the end of the section. Right. So for small Q square, right, we can measure this GE square, right, by just figuring out, oh, how does the cross section change, right, slightly as we change the Q square. Okay. To get to the magnetic part, okay, we're going to, of course, going to go to the other limit. Okay. So we're going to have tau much bigger than 1. Okay. What happens when tau is much bigger than 1? Okay. When tau is much bigger than 1, the cross section, okay. Actually, before we say that, I'm going to make sure that we understand how do we get to events that have tau much bigger than 1. Okay. So once again, right, we have the electron coming in with P1. Okay. And this is going to have P2, the proton coming out, and then P2 is the initial proton, P4 is the final state photon. Okay. In this case, what's going to happen is that we're going to look for events that are, have large scattering angle. So somewhere between that, right, and even up to 180 degrees. You're not going to get many events at 180, but you're going to get some events up to like 135 degrees, right? So somewhere between 45 to 135 degrees. So these are going to have a large Q square, right? Because remember, right, Q square is proportional to basically 1 minus cosine theta, right? So Q is proportional to 1 minus cosine theta, and then tau is proportional to Q squared. Therefore, if 1 minus cosine theta is large, right, in fact, it can actually get to positive 2, right, if you bounce back 180 degrees. Okay. Then, right, you're going to have taus that are, substantial. Okay, this is 2 mass of the proton square, right? Is it 2 or 4, actually? 4, yeah, because you squared everything. Okay. So in the regime where you have large scattering angle, okay, in other words, your Q is large, and then therefore your tau is large, okay. In this case, the cross-sectional limits is actually, right, if we take this again, right, we're going to have the tau part of your cross-section dominate. Let's go back up here just to make sure, right, go back to the original formula, right. So what's going to happen is that this term is going to dominate over this one, and this term is going to be not negligible, right? So what you end up with, right, is both, right, the cosine squared part and the sine squared theta part, okay? Where since tau is this number that's much larger, okay, this is going to be the term that's going to be dominating, okay? Right? In fact, what happened is that if you divide out the Mott cross section, this piece here, right? Okay, with a cosine, right? Let me just do it, right? Divide this whole thing, right? So alpha square 4e1 square sine to the 4th. I'm not going to do I just do theta square over 2, right? E 3E1, right? And then we'll do a cosine square theta here also, right? Okay, when you divide this out, what's going to happen is that you're going to end up with something that's going to be proportional to 1 plus 2 tau tan theta. The tan theta comes from the fact that you have sine squared theta over cosine squared theta. Okay, so tan squared theta there. And then you factor out this GM out in front. Okay, and therefore, right, if you measure the cross section of your events relative to the Mach's cross section, you're going to be able to tease out, this basically 1 plus tangent square theta aspects of this, okay, times whatever your magnetic form factor is supposed to be squared. Okay, and remember, just to highlight this, right, these are always functions of Q squared. Okay, we can actually see this when we see the differential cross section at different beam energy. Okay, this is actually data. It's from Hughes and Alt. Okay, you can actually see this in the data. Okay, so what they do is they set up an experiment. They have an electron beam coming in. Okay, and this electron beam, they can turn the energy up and down, right? And then they have a proton target. Okay, and so for in some events, basically they count what is the rate of this. So P1, P3, you got P4. Actually, don't even need to draw this because you never observe P4 anyway. So this angle here, right? If these electrons are coming out at 45 degrees, right? As I change the energy, so this is the dependent variable here, right? I go from low energy to high energy, right? So maybe you can't really get too low, like maybe 100 MeV up to about 1 GeV, okay? That's the energy range that we're dealing with, okay? And you just count how often do you get electron coming out at 45 degrees angle, okay? And that basically gets you this data point, okay? And then you do it again, you count how often does it come out at 60 degree angle, right? And then you get this line. How often does it come out at 70 degrees, 75 degrees? How often does it come out at 90 degrees? How often does it come out at 135 degrees? Notice that, right? No matter what, you are going to get a smaller and smaller cross section, and that's because, right, this 1 over sine to the 4th power, right? When you get to a larger scattering angle, that basically going to take you to 0. Okay. And in the homework, we're going to play around with a little bit of exercise to play around with these things, right? Okay, so hopefully they'll be useful for you to visualize actually how these data analysis method actually works. Okay. All right. By calculating, right, Q squared, right, from the angle, right, if you have the energy and the outgoing scattering angle, you can actually calculate what the Q squared is. Once again, this is another exercise we will do in the homework. Okay, you can actually, in this plot here, oops, I'll erase things, right? You can find lines of constant Q squared, okay? And that's what these dots here are trying to show you, okay? This is where Q squared is equal to 0.92 GeV squared. Okay, so why did they do that? Why we're picking a particular Q square? Okay, these constant lines of Q square, right, allows you to basically have a situation where the Q square is constant, right, and therefore, right, if you plot instead of plotting d sigma d omega over the Mach's cross section, okay, what we're going to do is we're going to plot 1 plus theta square of this. Sorry, not 1 plus theta square. Just plot this as a function of, tangent theta, tangent square of theta over 2. Okay, so why do we do this? Right, because if we did that, right, basically you have 1 plus 2 tau plus x times whatever the magnetic moment square is. Okay, this is just a straight line. In fact, you can see it right below us. Okay, all right. So this, when you plot this, your hope is that you're going to get a straight line, and the data actually shows this, right? So this particular point here, zoom out, right, came from over here, right? The next point came from here. The next point came from here. The next point came from here. The next point came from here, right? So basically what you're doing is you're teasing out information from one plot into another and plotting them first. Instead of plotting them against each other directly, you plot the tan square theta over 2 of this, and then what you should get is a straight line. And this is an extremely useful data analysis method called linearizing, okay? Because humans can spot straight line from miles and miles away, but then if you're plotting some tangent square theta function, right, that's more complicated to analyze. Okay, and when you do a fit to this, okay, right, you get a straight line, right? When you do a fit, then you're going to get the slope, right? Okay, the slope, okay, is actually going to be 2 tau times the whatever the magnetic form factor is squared, right? Right there, since tau, you can calculate tau using q squared over 2 times the proton mass, right? And this is for a particular, let me just write down what that is, right? Q squared over 2 times the mass of the proton. Oops, I keep saying 2, but then it's 4 because we squared everything. Okay, since this number is 0.292, right, this number is 0.938, right? That's the mass of the proton in GeV. This number is completely determined. So if you know the slope of this, you know exactly what GM squared is, right? Right. In fact, the y-intercept here, right, is this part. Okay. The y-intercept with that straight line will also tell you, okay, what GE square is, okay, plus tau GM square plus 1 plus tau, okay, because that came from all the way back. I should have more copies of this equation, right? That comes from this piece here, okay? Okay. So, right, in basically one set of data, you can actually determine what GM is, and you can determine what GE is, okay? And this is what the book is trying to show you towards the end here, okay? Right. So once you have these measurements of GMs and GE as a function of Q square, right? Remember, this plot is for one particular Q square, and then so you can make the same plot at a different Q square, right? You can just pick, this, maybe instead of this green, right? We can pick this dot. Well, we need more dots. Pick this dot, this dot, this dot, this dot, this dot, and right, that may be a series of lines that gives you a different constant Q square, right? And just by extending these things out, right, you expect that this will go out like this, right? You can do this even with where you don't have data points, okay? And then you can get, where you expect these data points to be, okay? And you can have it at different Q square, so an increasing Q square, okay? And what you can do is then use that to plot basically the GM squared, well, GM, okay, you can, as a function of Q squared, which will turn out to be this function here. And this is going to land exactly at 2.79, okay? And this is how this, this anomalous magnetic moment is measured to be exactly 2.79. There's more digits to it, to be 2.79, okay? And then GE is normalized in a way that it goes to exactly 1. Okay. Okay. All right. And that's how the these form factors are actually measured as a function of Q square, right? By just figuring out, at different, you shoot electrons into a proton, right? At different energy, so that's one of the dials you have, right? You can dial the energy and then see what angle it comes out at. And you can actually, through this analysis method, figure out what the magnetic and the charge form factor is. How much does the electron and the proton interact with each other straight from their charge versus through their magnetic coupling by just having, charges moving in magnetic field relative to each other that have spin. Okay. So from this plot, right, you can actually see that the magnetic form factor is 2.7 times more than the charge form factor. Okay. So once we set the charge form factor to have a normalization, it actually the magnetic form factor actually goes to 2.79 when Q squared goes to 0. Okay, so you can pick one of these to be normalized to some number, right? We could have picked, the magnetic to be normalized to 1, but then the electric will be, whatever 1 divided by 2.79 is. But we decided that it just makes more sense for the electric to denormalize to 1. Okay. So let's wrap up here. Okay. So at very, very high Q square, right, the electron proton scattering basically becomes a purely magnetic coupling. Okay. Right. In that case, right, what happened is that you only have the magnetic part, right? You kind of skip the cosine square theta part, right? What we can do is we can simplify this formula slightly. Okay. Okay. If we go back up to here, right? Let's go up to his formula here. Okay. Before we move on, let me describe where this formula comes from. This formula comes from, right, how this is a fit to this equation. These data plots here, right? Oops. Right. That's where this fit comes from. Okay. It's 2.97, right? So if you put in Q squared equal to 0, right, then you get exactly 2.79. Okay. Right. But then the rest of this 1 over Q square dependency, right, has a additional fit of 0.71. That just comes from this fit line. Okay. Okay. And from that, what you can do is that, you can say that, GM, right, as a function of Q squared, is basically going to be proportional to 1 over Q to the 4th power, right? Because you have a square here and you have a square there. They square to each other. In case of high Q squared, right, this is the term that dominates. So in the case that at very high Q square, in other words, very large scattering angle, like 135 degrees, what's going to happen is that, right, your momentum transfer, your cross section, let's see, just make sure we have this. Okay. So this part, right, you have, I'm just going to write out this factor here, Q squared over 2 MP squared. Okay. And then this GM part. This GM part, we're going to see that, this GM squared, so GM itself is proportional to 1 over Q squared to the 4th. So GM squared is actually proportional to Q to the 8th sine square theta over 2. Okay. Right. In this case, right, what happened is that, these sum of the factors of Q's cancel out. But what happened is that then, right, you end up with Q to the 6th power in the denominator, right? So when we're doing high energy, high Q square, in other words, the electrons coming back at a large angle, okay? The cross-section basically becomes whatever the Mott cross-section is, but with an additional factor of 1 over q to the 6th power, okay? So now, hopefully, maybe we can appreciate that, right? In order to get this data, right, you have to have a lot of luminosity. Remember that the number of events that you're going to get is going to be proportional to basically the luminosity, L, right, times your cross-section, right? Your cross-section is going down, right, by 1 over to the q to the 6th power, right? And therefore, you have to keep increasing your luminosity or collect data just longer. So you can see how these experiments could take years and years to collect enough data in order for us to get these data points, okay?